notice, those of you who showed interest in contributing to the writing of the lecture notes, you have been assigned to different courses. So you should contact, even present yourselves, no, and meet the corresponding trainers. Okay. And now we're going to start our second course or second lectures about statistics by Tommaso Dorigo. Thanks.
Yeah, so that you can see if I'm making faces. Okay, we are talking about statistics. In 4 hours, we can do only a brush off of a few things, but I hope that I will still be able to convey some important things I consider important that you can then deepen by yourself to study. This doesn't work though. Why doesn't it work? No. Was it this one? No. It's strange. Why has it stopped working? Maybe it's a matter of battery. Oh, now it works. Okay. For some glitch. Okay. So I present myself. I'm an INFN researcher in Italy. I work in experimental particle physics, and I have an interest in statistics, and now later in machine learning, artificial intelligence. So I have created a group that looks at end-to-end optimization of experimental design. I have a blog since 2005 where I've been blogging about particle physics. You can contact me, feel free to do so at these ways. I wrote a book which is sort of relevant to the things that we are going to discuss today. And you can get it for free if you ask me, okay? Two suggestions for this lecture. Interrupt often, please, because you may chance to ask a good one, and everybody benefits from it. And I don't expect you to follow all the maths, so that there is a little bit of it, of course. We have too little time for this, so I'll go fast, but of course, my slides are full of text, so you should be able to actually make sense of what is written on in, even offline. All right, so the contents of today. Why statistics matters. Why knowing statistics makes you a better physicist, okay? I'm deeply convinced that this is the case, and I will try to make the point. And also it will save you from horrible mistakes that you may sometimes make. We will look into error propagation just to make a couple of points, that it is not trivial, that you should look into it and understand it. We will look at the properties of estimators, which are fundamental for point estimation and interval estimation. So we look at the chi-squared and the maximum likelihood method. And we will looking at how you can choose estimators wisely, because they are a choice that you can make. And in the second lecture, we'll also look at ways to improve them by finding ancillary statistics. But for today, no, we will look at a simple case to conclude today. The case of making the weighted average of measurements when there is a correlation between them. This is a very common thing that you should be able to understand. And it's not by any means easy, okay? And that's actually counterintuitive, that we'll see. So statistics matters. To be a good physicist, you must understand statistics. Because typically, and I'm talking about experimental physics, typically our results are inconclusive. So we are always talking about the probability in probability terms, okay? So we have to use statistics because we typically look for rare signals. Rare signals are few events, and few events have particular distribution functions that you need to take into account. A good knowledge of statistics allows you to make optimal. Optimal is an important word, but you have to use it wisely, only when it is real, of your measurements. It's also easy to draw wrong inference from data if you lack some basic knowledge of, for instance, the density functions that the data are drawn from. This is common. Also, different statistical approaches answer different questions and therefore give different answers. So you have to be careful and know what kind of question you want to ask to your data in order to get the answer you do want. Okay? There's another point. As scientists, we have a responsibility in society to actually communicate our results in the correct way. So let's not use sloppy jargon, imprecise claims. I hear scientists, my colleagues, day in and day out making probability inversion statements. For instance, the probability of the data is such. No, we cannot talk about the probability of a process. Sorry, they say the probability that the standard model is correct is 99%. This doesn't make sense for somebody who throws a classical statistic inference. Okay, I made the point. So we will see some examples of this. I was saying that who talks bad thinks bad, and that I think is true here. I will make a list of things that you can encounter and that all have something bad in common. So I heard at the conference, this measurement is quoted as 0.12 plus or minus 0.003. So the effect is a 41 sigma proof on a non-null value. This was an astrophysicist. It doesn't make any sense to speak of 40 sigma because you will never control your uncertainties down to the tail of 41 sigma. It means 10 to the minus 300 and something. It's totally stupid to say so, okay? The probability that there is no resonance given the observed data is 0.0001. This is again probability inversion. You cannot say that. I expected 100 plus or minus 10 events from background. I saw 130. The probability that these 130 are all background events is thus 1.7 10 to the minus 3. This is not true. This is not the probability that these are background events. You're quoting the probability that you see 130 events if the background is 100. It's totally different. The cross-section is measured to be 1.5 plus or minus 0.5. So 1.5 is different from 0 by 3 standard deviation. No, because though that 0.5 includes systematics that do not have anything to do with the Poisson fluctuations. I tuned my selection by maximizing S over square root of B, so it is optimized for discovery. We'll have to say something about that. The upper limit is taken as the point where the cumulative of the likelihood function reaches the value of 0.95. The likelihood is not a density. You cannot integrate it. I opened the box and the event count was 3 sigma below the standard model. There had to be a mistake somewhere, so I changed the background estimating procedure, and now the measurement is within 1 sigma. Very good. But this is not blind analysis any longer. So, okay, just a potpourri of things that you have to be careful not to say or think about. So about sigma over square root of background, and this is still a means of introduction, okay? This is typical. You do counting experiments where you look for photons from a source in the sky, for instance. So you have a certain expectation from your background, which you get by looking off the source. And then you look for a signal that might be on top of it and therefore contribute to the Poisson mean. So this is the typical counting experiment where you can say, okay, I optimize for S over square root of B, where B is the number of expected events, and I have some Monte Carlo that tells me how the signal should behave. Even if you don't have any systematic uncertainty, so you know the predicted background precisely, it's a Poisson process. So the background will have a typical fluctuation which goes with the Poisson. So the variance is equal to the mean. So typically one says, okay, then if I have a signal on top of it, then signal over square root of background fluctuation. So that would make the strongest inference, right? But this is based on approximating uncertainties for the Poisson with a Gaussian distribution and fails in small number of events. So that's a very quick example. I don't want to waste time on it, and we'll go into the real program of today. But I am in the CMS statistics committee, and we screen results from physicists, and there's always some evangelization to do, because people come in and they know the physics, but they don't know the statistics, and they have to do more statistics than physics when they come to do analysis in CMS. And so a guy was saying, oh, I found a great cut of my data that increases the observability of the signal, because I go from a signal over square root of b of 8 to a signal over square root of b of 10^2.7. Well, go for it, right? Because you increase your quality factor. Is it a good idea? Because the numbers are small. You expect 8 signal events from background event. After the cut, you expect 4.8 and only 0.2 background events. Should you take this route or not? In fact, the median, which is the right thing to look at, of the background only p-value distribution when you expect 9 events is the background probability 1×10⁻⁶, which is twice smaller than the median for observing 4.8 plus 0.2 when you expect 0.2. So you have worsened the expected p-value of your search by a factor of 2 by making the cut. So you see that you have to be careful, okay? Because this is a real analysis, and this can happen. Okay, so I think I made my point, right? Be careful about these things. So let's warm up our muscles first. All statistics books start with discussing probability density functions. And that is for a good reason, that you must know them. Because if you don't know the statistics distributions you're sampling your data from, you are going to be in trouble. So I think all of you probably know what's a Gaussian or a Poisson or an exponential or a uniform or a binomial or a multinomial. I hope that we are not in the need of discussing this, right? A mediocre particle physicist lives a comfortable life without knowing other things. But I think that you should at least know these, but even more than these, because they do happen in your data. And you may be in the situation where you need to realize that your data are sampled from these distributions. And there are many others. We have no time to go through them, but you should look at them. Let's look instead at a pitfall, what can happen if you mistake one distribution for another. So let's start with the Poisson. The Poisson is a probability, a distribution function, which has integer support, right? You know that the expectation value of the Poisson is equal to its variance. And it describes the probability of getting exactly n events in a given time if these occur independently and randomly at constant rate in the given time. It's crucial that the rate is constant for the Poisson to be true, okay? Okay, other fun facts, but it's important that you realize what the properties of the Poisson are, because you may not be in that situation and think that you are and draw wrong inference. Practical examples, I will not go through this, but well, we can even go through this. It's an example. Is this a Poisson distribution? You walk from office to home to office every day, and you do always the same road. And other things being equal, you should cross more or less the same number of people on average, okay? And this will come in at some constant unknown rate and random. So you can collect some data of the guys you meet in the street. Is the data coming from a Poisson distribution? So even if everything else was constant, there were no vacations, no particularities in the week. The fact that sometimes people like to come in groups, and you don't meet one person at a time, but sometimes you meet 3 persons at a time. Is this changing the probability distribution function? So you may invent a statistical test to determine if the distribution is indeed a Poisson, and you can leverage the fact that the mean and the variance of a Poisson are the same. So you can test something with the data. Is the variance equal to the mean? We will do a hypothesis test tomorrow, but you can, in fact, run this experiment, and we will find most likely that the data don't come from a Poisson distribution. what is the distribution that they come from? I'm spoiling it. You should do the test, but it's a compound Poisson distribution, okay? The compound Poisson distribution describes the sum of n Poisson variables, all of mean mu, when n is also a Poisson variable of mean lambda. So you have the convolution of two Poisson processes that add up. The expectation value is lambda times mu, and the variance is lambda times mu plus 1 plus mu. And you see that there is an uninvited guest here that makes the Poisson variance and the compound Poisson variance different. And in fact, the compound Poisson has a larger variance. And this makes all the difference in what we'll see in a second. So, can I ask you how many of you knew the existence of the compound Poisson? Raise your hand. Really? Well, it's not uncommon because typically less than 10 or 5% of scientists know the existence of this. And it's very bad because it happens that they publish on PRD completely false claims because they don't know that the compound Poisson exists. These guys in 1969 published, they were looking for tracks in a bubble chamber image, and they saw tracks that had very little ionization. And you know, in 1969, people had postulated the existence of quarks. Quarks have a fractional charge. They ionize less if they exist as free particles than ordinary unit charge particles. So these guys published a paper where they show the track which could not be anything but a fractionally charged particle because it produced, normalizing things, 100 counted droplets per unit path length against an expectation of 229. So really smaller, okay? So the point here is that it's a Poisson process, the ionization, because you have random bumps with the atoms that ionize the atoms of the gas. If you are strong in nuclear physics and you are strong in thermodynamics, you may know that the scattering interaction, in fact, on average, produces about 4 droplets. The scattering and the droplet formation are 2 independent processes, and they are both Poisson. So there you have it, a compound Poisson. Okay? But if you don't recognize that the compound Poisson is different from a Poisson, you end up publishing on PRL a completely false claim, because the significance, and here we will take tail probabilities because we are doing classical statistics here. And in fact, let's count the probability that a Poisson of mean 229 ends up on the wrong side, so produces at most 110 droplets. This is what a classical statistician does. You draw your probability density function and you say, what is the probability? Well, I have observed this value here. So what is the probability that I should observe such an extreme value, because the mean is here? Well, you can answer this question by looking at data that you haven't collected. This is what frequentists are mocked by Bayesians by, because they, to get the p-value here, they look at the integral from 0 to the value that you observe of the PDF, okay? And so we are going to do that here, and we say we saw 110 droplets. How extreme is this probability? It's 10 to the minus 18. It's impossible. It doesn't happen. But they observed 55,000 tracks, so you have some variability. This is called trials factor, or look elsewhere effect, or Bonferroni correction you have to apply. So you have to take that into account, and you do that by calculating 1 minus p to the 55,000. So you correct this small p-value for the fact that you're doing multiple testing. And you get 10 to the minus 13. The conclusion doesn't change. This is not happening if this is unit charge particles. So they publish, okay? But it's a compound Poisson process, not a single Poisson, with lambda mu equals 229 and mu equals 4. And you remember that 1 plus mu in the variance term, that makes all the difference, because now the probability should be computed as this. And it is 4.7 10 to the minus 5, which once you compute the trials factor becomes a probability of 92%. So here are two physicists who made a claim on PRL, and they made the p-value wrong by a factor of 10 to the 12. Okay, so pay attention to your PDFs. Okay, and it doesn't matter if you know the physics well, of course. Okay, since we are at it, let's list a few properties of very common PDFs that you may encounter. And so we know the Gaussian, we know the exponential, we know the uniform distribution, the Poisson. They have means and variance that you should know by heart. There's stuff that you can read about this distribution, and it doesn't hurt. Okay. So I'm not making any specific point about this, only just listing them to show that this should become your friends. Okay, if you are doing that analysis, this really should be at your fingertips. Okay, so let's talk about point estimation. We combine measurements into an average. What we are doing is point estimation. And in fact, combining measurements is a part of fitting, if you want. You are fitting a constant through some points, in a sense, okay? It's a common problem, and it's not easy, because sometimes when you have correlations between the variables, in fact, there's people that still publish new ways to combine measurements with correlations. It's fun. It's not solved. It depends what kind of questions you're asking and on the details. But okay. So in statistics, this is rather called parameter estimation, point estimation, and interval estimation. They're two separate things. And in fact, tomorrow we'll discuss coverage and interval estimation. Right now we discuss with estimators and point estimation. So we start, of course, with a probability density function, which is a normalized function that describes the probability that you find a certain random variable in a given range. And this is defined for continuous variables, but of course you can define it also for discrete ones. Even we have encountered the Poisson a moment ago, which is an example of that. You know what the expectation value of a random variable is, and we call it the mean. And it's crucial what is called the second central moment of x, which is the expectation value of x minus its expectation value squared, which you get by this formula, and we call it the variance. And okay, the variance, you can compute it this way. And we typically use the standard deviation as a proxy, right, the square root. So the parameters of a probability density function are some constants that characterize its shape. So for instance, this probability density function is theta, and it's characterized by the parameter theta, which gives it a certain slope. But I made a mistake here. This is not a probability density function. Why? It's not normalized. In fact, this is a probability density function, okay? Suppose that we have a sample of observed values, random variables taken from that. We often want to find some function of the data that estimates the parameters of this probability density function. This is an estimate problem, right? Estimators are functions of the data that allow us to draw estimates based on specific sets of data. Okay, so the estimators get a hat because they are nobler, okay? They're more general. Two properties of the estimators. Let's take an experiment. We collect some data and we draw some inference with the estimator. If we get to repeat the entire measurement many times, and today we can do this with our computer, simulating these things, we know that the estimator itself can be considered a random variable that takes on a particular PDF. And if we study that PDF, we get to know what are the properties of that estimator. So an estimator, we may find that if you have a true value theta, it can cluster around it very well, or it can cluster around it with larger variance. This is the variance of the probability density of the estimator given 10 measurements, okay, of X. So you can have a small or large variance estimator, or you can have a biased estimator. In statistics, bias and variance are the two things that you have to try, and you want to squeeze the bias to 0 and you will blow your variance, and vice versa. You want to squeeze your variance and you will get a bias, because these two things are competing. Okay. So the bias is defined this way. So for a good estimator, the average of repeated measurements should tend to the true value. So the bias should be small, and we want small variance, okay? And then we have the covariance matrix, and we can define correlation. If you have two, you need at least two variables, random variables, then you can define their covariance by the expectation value of this expression, and you can work it out to be this one, okay? That's very simple to show. And this allows us to construct a covariance matrix, which is a symmetric matrix with a positive defined diagonal elements, which are the individual variances of the two measurements that you are combining in this two-dimensional example. And you have a number R here, which is defined as the correlation coefficient by that formula. And it's a number that tells you something about how the variables influence one another. But it's a weak condition that you have R equals 0, the variables are uncorrelated. It doesn't mean that they are independent. The variables are independent is a much stronger criterion, okay? It means that you can construct a two-dimensional PDF as the product of two one-dimensional PDFs. Then R is equal to 0, and the expectation value of their product is this. So, and the covariance matrix is indeed diagonal, and this cancel. But the fact that the expectation value of xy is equal to the product of the expectation values is not a sufficient condition for the two variables to be really independent. Okay, be careful to say that variables are uncorrelated when you mean independent, and vice versa. They are two different things. Okay, and here is a nice graph from Wikipedia to exemplify this. Here is the correlation coefficient of some clouds of data, and you see that you have several structures here which will all give you a 0 correlation coefficient, but they're not independent by any means, right? How am I doing with time? When did I start? Okay. Okay, so we can slow down a little bit. It's fine. So, and then there is this construction called the arrow ellipse that is a good visualization of two-dimensional point estimates. So, imagine that your parameters are two, theta, let's call them theta 1 and theta 2. So in the large sample limit, typically everything becomes a Gaussian. So in the large, if you have lots of statistics, their estimators will be distributed according to a two-dimensional Gaussian. And therefore, this allows you to draw an ellipse that is more or less a 1 sigma away from the best estimate circle that you can draw by looking at the likelihood at its maximum. We'll talk about the likelihood in a moment. Unfortunately, I probably should have done that first, but when you step a half of unit away from the maximum of the likelihood, this allows you to draw a contour of all the values of theta j and theta I that have the likelihood equals to this value, and so you get a way to show that the two variables are correlated because this ellipse has a tilt, okay? And also to show what is the variance on the two measurements. And you see that in this case, theta j is measured less precisely than theta I. And then you have other things also to note here, because you get to know what the correlation coefficient is, and geometric construction is such that the correlation coefficient rho times sigma I, which is this quantity, is equal to the distance from this point tangent to the vertical line of the ellipse to the center axis. So there's a number of things to say about this construction. Okay, but this is quite standard. I would invite you to look at a nice place that summarizes things that you may be useful to you, such as this. It's the statistics review chapter of the review of particle properties. It's online, it's for free, and it's very well groomed. So, okay, I don't want to make too many points about this, but it's a nice way to visualize how things are in terms of these two variables. We will use, in fact, the correlation of two variables when we want to take their weighted average in a moment. So, error propagation is another important instrument for us, because we typically measure some random variables, and then we want to derive some inference on some derived quantity. So, for instance, you have variables xi, and you don't know what the PDF you're sampling them from is, unfortunately, but at least you know their mean. You can certainly compute an estimator for that, and you know, say, the covariance matrix they are sampling from. And you want to draw some inference on a function y of the xi. You want to determine its PDF. In order to do that, you can expand in Taylor series around the mean of the x. So you will have y of x is more or less equal to y of mu plus the sum of the derivatives times the distances, okay? And this is to first order correct and allows you to have a model for y. If you get that, you then can show that the expectation value of the y's and the y squares are respectively this and this, where here you recognize the second term in this expression as the variance of the y's itself. As we have seen before, this is the formula. And you can do this also in multidimensional fashion if you have a set of functions y of x, because then you can build the covariance matrix of the y's themselves, so the U matrix, which is just taking all of these for the various y k's. Okay, this defines the covariance matrix of the y's. And this allows you to do fancy compact notations for chi-squares and other things that you can compute by matrix multiplication. For instance, you can write that U is equal to the matrix of derivatives times V times matrix of the derivatives transposed, where these are the YKs. So all of these mathematical construction looks cumbersome, but actually allows you for some synthesis in that you can then express chi-squares in a very compact way, and we will see an example later on. But it all rests on the assumption that you can expand linearly in Taylor series. And this is not a trivial statement to make. Sometimes it breaks down, and sometimes the approximation that you make may not hold up in your particular case. So you always have to check that these approximations that you are making implicitly, because at some point we forget where some expressions come from, but you have to go back and check, because for some particular case, your numerical example will be extreme enough that you get to make wrong inference from your data, okay? So let us put this to the test and see how this works. These, of course, are trivial examples, but they are meant to just make a few points, okay? So the variance of a single y of x, now let's go back to the one-dimensional example. Here's this formula here. And let's take the sum of x1 and x2, or the product of the x1 and x2, and let's see what this boils down to, okay? So y is x1 plus x2, so the sigma square of y is the sum of the individual variances plus twice the non-diagonal term. Okay, this is just the matrix multiplication. And for the product, you have to fiddle a little bit more to find that it's advantageous to divide by y, which is x1, x2. So you get that the relative variance on y is equal to the relative variances of x1 and x2 plus the relative covariance term for the product of x1 and x2. Okay, so this is the way it works, and it's nice and tidy. So let's put this to the test. So for uncorrelated variables, again, if the covariance term is 0, you see that in the sum of two components, the variances add linearly, while for products, the variances add multiply, or sorry, the relative variances add linearly. Okay. So now this brings us to try a simple example of how this works in a practical case. So let's take a scale, and let's imagine that you have to weight two objects, and you have time for two measurements because measurements are expensive. Okay, and these objects A and B. And this is a 2-arm scale, and you know, you put the weights on one arm and you level it off. What is the best way to do this? Does anybody have an idea? You should remember how error propagation works. And it's a joke. I cannot really ask this question because if you have not seen this, probably you would not come up with the right answer. The right answer is not to weight A and then weight B. Because every time you weight an object, the other one is staying on the table begging you to participate. You are losing information in the process. So if you weight separately A and B, and the scale has a constant error, which is the smallest weight you can put on one arm, of course, 1 gram, the uncertainty on A and B weights is 1 gram. Okay? But if you instead decided to weight the sum of the two objects, or the difference of the two objects, by first placing both on the same arm and then placing one in the one arm and one in the other arm, error propagation tells you that the uncertainties on each become 0.7 grams. There you have increased your precision by 30% out of nothing, okay, by knowing error propagation. All right. So this is the result of having made the best of your measurements, having let both weights participate in the two weights, okay, in the two estimates. And this changes, of course, if you have a fixed percentage error, but this kind of scale doesn't have a fixed percentage error, but other kinds of scale might be in a situation where instead errors propagate with the product. And then you get a different situation, and you have to decide when it is correct to do something or do something else. But you see that the point I want to get here was that if you know a little bit of statistics, you can design better experiments. And so you have the same data of your fellow down the corridor, and you get 30% better uncertainty with the same coverage. So it does pay a dividend, okay, if you know these things. Okay, that was the point I wanted to make. And let's come to the weighted average. First, when there is no correlation. So we have to combine two different independent measurements which have variances sigma 1 and sigma 2 of the same physical quantity, x0. And x0 is the mean of a Gaussian measurement with a sigma I, which are different for the two measurements. So we denote them of x1 sampled from this Gaussian and x2 sampled from this Gaussian. We want to combine these two linearly to get the result which has the smallest possible combined variance. So your question is, the question for you is what are C and D such that the combination uncertainty is the smallest? How would you go about solving this problem? Smallest sounds of having to take some derivative, making a differential measurement, okay? So first of all, you take this and you note, okay, I have two parameters, but really, I know that D has to be 1 minus C because otherwise I violate the unitarity, okay? And then we can express the variance of the combined measurement, which we haven't yet done, but in terms of the variances of x1 and x2, because you take this expression, and then you can do error propagation on this. And then when you have this, you can just take a derivative, find the C value that minimizes the expression. So you take a derivative with respect to C and set to 0. Okay, and you get this, and you get this. So you get the values for the weighted average and the uncertainty, which are what is on every textbook, and you are comforted by your added wisdom, okay? But we will revisit this with correlations later on. But this is correct. It's a way to proceed to make the average of two independent measurements of the same quantity if they are not correlated. So before we go to that other part, let's linger a little bit on discussing estimators, okay? Because there's a number of things that we can note about them. So again, we will take a sample of observations xi, we call them IID, independent, identically distributed random variables. Okay, and you can construct a statistic with this data. A statistic is a function of the data, okay? And the statistic doesn't contain any parameters that you don't know about in this case, okay? So it's just something that you can compute straight away when you have your data. You can make them complex as you wish, of course, but that's the bottom line. So an estimator, as we defined already some, is a statistic, in fact, which is used to estimate some property of a PDF. It is a statistic. Using it on some data provides an estimate, and we have said that. One property of estimators is that they can be consistent or inconsistent. A consistent estimator is one that converges to the true value of the quantity they estimate for large data. So consistency is a good asymptotic property, but we seldom do much with it because we usually are far from asymptotia, okay? We always have to deal with small data sets. Otherwise, everything is very much easier, okay? You can approximate things with Gaussians, you can take limits, you don't have to worry about the sampling properties. It's all a dreamland, but we are never there, unfortunately. And the expectation value, okay, I didn't bring myself to make this an equation, so there's an asterisk instead of a hat. So may the estimator pardon me for that. Once you have an estimator, you can get its expectation value if you have its sampling distribution, of course, because you have to integrate over it, okay? And there's nothing new about this. One simple example of an estimator is the sample mean, and another is the sample variance, and you can derive them from data that you collected, and you first get the mean as this, and then you get the sample variance by this formula. And this is an unbiased estimator of the population mean and the variance. You have to have this -1 at the denominator in order for it to be unbiased. It's a demonstration that it's in the backup slides, but I don't want to bore you with that. But in general, we said what the bias is. And a fun fact is an estimator can be consistent, that is, have these good asymptotic properties of converging to the true value for large n, even if it is a biased estimator. So you have a bias that goes to 0 as n approaches infinity, but it's never 0, okay? So biased estimators are not as bad as inconsistent ones, in the sense that we often have to work with biased estimators. We only have to estimate the bias if we can, okay? Other important properties of estimators, which you have better know that they exist, is efficiency, is you have a class of possible estimators that you can construct, and the one that has the minimum variance is efficient within that class. I don't have an example for this, however. Robustness is also a very, very useful property when you are not very sure about the sampling distribution, and therefore there may be systematic uncertainties. We are often in that situation when you are modeling things in fundamental science, so if you construct a robust estimator, that will work well, in the sense that it will be decoupled from the systematic uncertainties more than a less robust one, okay? I have an example for this, and I will show it to you in a little while. More properties of estimators. One important quantity that you will want to minimize, well, if you do machine learning, and I bet most of you have tried to train a classifier at some point already, you typically want to minimize a quantity that's the mean square error of some quantity, if you're doing regression, for instance, because this is really the quantity you want to bring down, and it's again, it's the sum of variance and squared bias. And I was saying that these two things are competing, one versus the other. You can construct estimators that have a smaller variance, but they have a larger bias, and so on. Okay. So this is what summarizes it all, because you need a metric to decide whether you want to squeeze the variance and let the bias grow or vice versa, and that is the proper metric, because in the end, the mean square error will tell you how far off you are with your estimate from the true value. It is the squared sum of those two things. And then you have the other tool that you use is the Rao-Kramer-Frechet bound, which gives a lower limit to the variance of estimators, biased or not. It arises when you are trying to maximize a likelihood, and I will show the expression later. I said this, I said that, and we will look at two estimators that are the maximum likelihood estimate, MLE for friends, and the least square estimate, LSE for friends. Okay? Okay, we said this, I don't need to repeat things. So let's go to the maximum likelihood. I bet I'm saying things that you all know very well. So, and even if you don't, you find them in any textbook. So we will be quick. But anyways, you need to start with a PDF. If you don't have a PDF, you cannot do a maximum likelihood approach, because it's based, it's intrinsic in the construction of the likelihood that it is the product of PDFs that you're sampling your data from. Okay? In fact, you can write the likelihood function, and I'm saying this is not a density function because it's a function of the unknown parameters that you want to estimate. Once you have collected your data, you can write the function of the parameters. You cannot get your likelihood if you have not collected your data yet. Okay, and that's because the likelihood is to be interpreted as a function of the parameters, such that you can maximize it to find the maximum likelihood estimates of the parameters. The the integral under the likelihood is meaningless for a classical statistician. Yes, I know you can multiply the likelihood by a unit prior and then you get a posterior, which is a PDF. But you have multiplied the likelihood by a PDF to get a posterior, okay? So the likelihood is a function of the parameter. Knowing this, in fact, can avert some pitfalls, such as the one I was discussing at the beginning. So using the likelihood, one can define the maximum likelihood estimators as the values that maximize the likelihood, which are solutions. So if this is multi-dimensional, they will all get their own small hat of the equations that are defined by taking the derivative with respect to them, okay? So you see that the method that estimates the parameters is simple, but it requires you to input the PDFs. If you don't have the PDFs, you cannot use the maximum likelihood method, okay? And then we have the variance, which is obtained by taking the inverse of the second derivative of the likelihood at the maximum, okay? So that is an estimate of the variance. It's not the variance itself, okay? It's an estimate of the variance of the estimator. And this is actually not even precise, because it's only a lower limit of the variance, which only applies to conditions which are very special, that is when there is no bias. In general, when there is a bias, you can get a lower bound on the variance. At least you get to know that the variance is at least as large as that when you have accounted for the variation of the bias with the parameter. And this is called the Rao-Cramer-Frechet inequality. Okay? Yeah? Can you construct? You can use other methods. You can approximate the likelihood by taking, for instance, one of the ingredients, you don't know the PDF, you can use a Gaussian around a certain estimate of the mean. But of course, all your inference will be dependent on how good your approximation is. But mind you, we do this day in and day out, because in fact we rely on approximated PDFs to do our day-to-day inference. And in fact, when we do this, we estimate a parameter with the maximum likelihood method. And then we have to go back and say, okay, but I have systematic uncertainties, because now I have my Monte Carlo, and my Monte Carlo was tuned to a top quark mass of 172 GeV. What is if it is instead 175 GeV? Then your PDF of the data is changing, and then you have to propagate that change into your result and see how much of an impact you have. So this kind of two-step procedure, in fact, is highly suboptimal in a sense, because if you do machine learning, you try to optimize a certain, for instance, a classifier, and you optimize it based on PDFs of signal and background. So it's basically learning the likelihood ratio of some two distributions. So we are not far from this. And if you have an uncertainty on the distributions that you start with, then your optimal inference is not optimal any longer, because when you consider the systematic uncertainties in the PDFs you have used to train your classifier, then you get a significant increase in your uncertainty bars in whatever you are getting from your classifier, say the signal fraction in a two-dimensional, in a two-component mixture model or something. So what I'm trying to get at is that, yes, you can do it, we do it, but you pay a price for it. It would be better if you were able to either, well, know your PDF better, or find a reparametrization of your data on which you can model the PDFs better. Because sometimes you can rotate away from systematics in a way that you get insensitive of the top quark mass on this other variable that you have extracted, and then your inference is more precise. Okay, so, but yeah, in general, you can use whatever, but you know, garbage in, garbage out, okay? So the likelihood is nice because you can actually try at home some examples, and here is one for you. You can, well, it will be spoiled anyways because we have little time. These are parts of some lectures that I do when I have also practical examples, and people are invited to code problems such as this. So take a die, and the die has 6 faces, and so it can give you 6 numbers, and so it's a discrete problem, and therefore the likelihood is easy to write. And you can write the probability of each die throw as 1/6. But if there is a load, or somebody has put some lead on the 1 such that the 6 come up more frequently because the lead will go to the bottom, then you can model it by saying, okay, the probability of the 6 is larger by a parameter t, and then the probability of 1, which is opposed to the 6 on the die, is smaller, and then maybe the ones on the side also get decreased by a single. This is just a model for what would be the behavior of a die where one had put lead paint on the 1. Okay, and so you have some data that you control this die 20 times because we don't want to get old by doing this, and you get a few trials. You get 3 times a 1, 5 times a 6, and 3 trials each, and with a 2 or a 5. So you can write the likelihood of this because you know the probabilities, so it is simple. And you can actually already take the logarithm of the probabilities, and it is a sum instead of a product, and it's 3 times this minus 12 times this plus 5 times that, 12 because it's 4 times 3. Okay, so you have a likelihood, and you can differentiate, and you can extract the value of the parameter t which you want. I have not disclosed the quadratic equations values for you to be able to actually do something at the lunch break. But it's nice. It's a quadratic equation, and then you have a solution in the allowed range, which turns out to be in this range, and okay. And then you can do the second derivative of the likelihood, and you get also an uncertainty, which is a likelihood interval. We will talk about the coverage properties of likelihood intervals tomorrow. But okay, you get 0.072 plus or minus 0.084. So with this data, you cannot conclude that there is a load on the die. Given that those data, we will do hypothesis testing tomorrow also. But okay, this is the point estimate of the load. It is different from 0, but not too far from it. So that's the conclusion that you can already take. Okay, so the nice thing about this is that you can code it in a small root macro or whatever other code you want to use, and then you can do this a gazillion times in different conditions and test coverage properties of likelihood estimators and have fun with it. Okay, but okay, this is an exercise that you can take if you want, and this will be the basis then of studying the coverage properties of likelihood estimators later on. Okay, so now the other typical estimator that people use for point estimation is the method of least squares, and at a variance with well, variance is a loaded word, but anyways, with the maximum likelihood method, the least squares method doesn't require you to know the PDF that you're sampling your data from. And that's the main getaway point, but we'll get to see that better later. But okay, let's imagine now that you have a set of measurements yi that we assume are Gaussian random variables. We assume that they are Gaussian because we don't know the PDF, and the best bet you can take in most circumstances is the Gaussian. Not always, okay? Sometimes you will want to use other things such as a uniform distribution. But okay, in this case, you want them to be Gaussian random variables, and you want them to have different unknown means. And well, you assume you know the variances at least. So this is basically your data. So the data has certain values of y as a function of x, okay? And you can consider this as a vector that's a multidimensional Gaussian, which depends on the true values and on the variances, and you can write this as a multidimensional Gaussian. And you see that there is no correlation term here. These are independent variables. So, and then you let lambda be a function of this parameter x. So lambda is the model that you want to fit through the data of this y as a function of x, okay? And you want to find the parameters theta of this model lambda. And so you want to cook up some estimates of the parameters theta. So we can take the logarithm of this joint PDF, and we get the log likelihood function. We know how to do this, and that is the logarithm of the likelihood. And you see that it has this nice form, which indeed is maximized if you maximize this sum. It is maximized if you minimize this sum, sorry. So you see that if I define the chi-squared as this function, I see that it's derived from a Gaussian likelihood, okay? So the two things are one-to-one. And in fact, this is a standard definition of the chi-squared. You have the yi, and you have the model, and you take quadratic differences divided by their variances. So this is the chi-squared for a simple parameter theta. And this expression has a chi-square distribution only if some conditions are met, but I won't bore you with these details. But this thing is that this method works, that by minimizing the chi-squared, you can extract the parameters theta, given some data. Also, if the data are not sampled from Gaussians, so the uncertainties are complicated, whatever. That is, it has some robustness in it because it relies on the good properties of the Gaussian. But it still will have worse properties than a full likelihood written with the right PDFs, okay, of course. So if the measurements are not independent, then you have a joint PDF, which will be an n-dimensional Gaussian, which becomes a multivariate object with more complex properties. But you can still write this expression where you see you take the deviations and you combine them with the covariance matrix, and you get the chi-squared. And this still holds even when you have correlations. And in fact, we are going to use that very expression in a moment. So the point here is that writing the chi-squares only requires an unbiased estimate of the variance of a distribution to work. And this is nice, and it's bad. It's nice because it simplifies you a lot, the work. It is bad because it is an approximation that can fail in some situations. So let's see a situation when it fails, okay? And let's take the business we do day in and day out in particle physics and astroparticle physics and neutrino physics, whatever. We have counters, and we count events, and we do counting experiments. So in this case, we are counting from some radioactive sample. Okay, it's not Poisson, it's binomial, but we can approximate it with Poisson, okay? You have 3 readings in 3 different equal time intervals, 100, 90, and 110. So you look at these numbers and you say, okay, well, the variance is equal to the mean, so these are all within 1 sigma to one another, so I can combine them. This is an important first step that you have to make. When you want to combine some measurements, don't do it if they are inconsistent. You can apply special procedures. In fact, the PDG offers you a procedure where you blow up with scale factors some of the uncertainties in a combination of different values if they are inconsistent. When they are very inconsistent, the result of an average, or a weighted average, will make absolutely no sense, okay? So be aware of that. But in this case, you can do it. And these measurements are compatible, so you take the average, and the average is, of course, 100. and you can compute the uncertainty on the average, and that is the number you get. All is well here, right? Now, imagine that instead you were lazy and you decided that you want, or maybe you didn't have only 3 measurements but 27. You wanted to do this by doing a fit to a constant. So you put these measurements on a histogram and then you draw a constant line. So the constant will tell you what is the weighted average of this measurement. So you expect that if you do this, you will find the same result of the simple average of the 3 numbers, right? But that is not the case. If you do this under root, which uses the Neyman chi-square to do the fitting, you have 3 numbers here, 3 Poisson variates. You do the chi-square fit, and the chi-square converge to 99.33. It's biased low. Okay? So the chi-square doesn't preserve the area. This is the jargon sentence that we say. And instead, if you do a likelihood fit, which in fact only requires you to specify capital L between brackets when you do the command that fits, not much of a problem, you get the right result. But what is going on? What is going on here? Why really? Where does this negative bias come from? You know, estimators can be biased, and this is an example. Okay, let's look into it. So you will notice, first of all, that the chi-squared statistic results from a weighted sum of squares. A weighted sum of squares where the weights are the inverse variances. And the inverse variance and the variances of these measurements, they are estimates. We don't know the real variance. We estimate the variance as the value itself because we know that it's a Poisson. So a small variance, because the number is small, 90. This guy weighs more than this because it is smaller, so its variance estimate is smaller also. So there is a negative bias in the chi-squared. In fact, let's look at this more analytically. You actually have 2 Poisson chi-squareds that you can define. And this is the one we were talking about, where you put the actual counts as a variance, because you say this is a Poisson, this is 90, then the variance is 90, okay? Poisson's does a different thing. It says, okay, I have a minimization job to do anyway, so here I will put the best value that I will get, and I iterate and I get it, I can derive and obtain it. So it's different, right? And then, so the Poisson's chi-square uses the best fit variances, this using the estimated variances. They are both good, asymptotically they're consistent and everything, but they use approximate weights. They don't use the real variances here, and this results in a pathology, okay? Because neither of these definitions preserves the area. In fact, this is an underestimate and this is an overestimate. Instead, if you maximize the Poisson likelihood, but you see that in its belly, the likelihood knows that these data are coming from a Poisson distribution, preserves the area and obtains exactly the result of the simple average. And this is proven here. Let's try first from Poisson's chi-squared. It's simple, right? You take a derivative and you set it to 0. And you get this funny result that the best estimate is the square root of the average of the squares of the components. What the hell is that? It is whatever it is, but it is proven mathematically that this is an overestimate of n, okay, or of the true value. And let's look at Neyman's chi-square, where you can take the derivative with respect to the value you want to find, and then you get this. And you can solve for n, or you can do some fancy combinatorial trick. But in the end, you get that it's the harmonic mean of the inputs that you get out. It's not the arithmetic mean. God damn it. So it's an underestimate in this case, and also proven mathematically. Instead, if you do the Poisson likelihood, well, you just take the logarithm and you set to 0 the derivative, and you get the the result you wanted. So likelihood fitting preserves the area. Okay, and that's why you should use a likelihood if you at all can. So let's put it together. I did a small pseudo experiment toy generation for you to see what happens in asymptotic terms. So what I did was I filled a histogram of 100 beans, so I can do actually the fit of 100 different Poisson numbers. 100 beans, each of which is sampled from a Poisson of mean mu. And I will then change mu and see what happens. And I fit this histogram to a constant by minimizing in turn these three estimators. And then I generate another histogram, again sampling from the mean, and again I fit, and again I estimate the value, and then I check how well they reproduce the value mu that I input, okay? And I study the ratio of average result to the true value. So I want this ratio to be 1, and I can study it as a value of mu itself. So you see that as a function of the true value of mu, and this is done by repeating pseudo experiments many times so that I can get a precise estimate of the bias here. You see the Neyman's chi-square has a 10% bias if your entries in the histogram are 10. If mu is equal to 10. So people have often told you the Poisson will converge to a Gaussian when n is large, mu is large. How large? Well, 10. No way, okay? 25, no way. No, I mean, you will still get a bias even for large. I mean, the Poisson is a different distribution from a Gaussian, for God's sake. It's a discrete distribution, not a continuous one, okay? So beware. And beware that also the smartest chi-square that Pearson's cooked up is also biased and not by a small amount, okay? So if you want accuracy, you should get a likelihood if you at all can, okay? And also be aware that your friend Ruth uses the worst of the three estimators. If you don't, it's lazy, okay? So discussion, I think most of this we have already said at this point. What we are doing when we fit a constant through a set of k-bean contents is to extract the common unknown true value from which the entries were generated. These are Poisson. They should have the same weight because they are drawn from the same mean, but we cannot do this. So Neyman says, let's use the values that we get. Pearson says, let's use the fit result. Okay, so I said this already. The Pearson, the Neyman's chi-squared is downward biased because low-lying results will weigh more in the average. The Pearson's chi-square uses a common weight, and this is also an estimate of the true variance. And the denominator in the Pearson's chi-square is the fit result. And since we minimize the chi-square is smart. It increases its denominator so that the chi-square goes down, so that you get a larger value. Increasing the denominator means increasing the true value that you're fitting. So that's why you get a positive bias. Okay, so all methods have optimal asymptotic properties, but you never are in that case. So whenever possible, use a likelihood. That's my bottom line for this part, okay? And now let's say a few more words about point estimation. How much time do I have left?
We are now the second hour.
Okay. Can you bear with 40 minutes, or do you want to take a small break? For me, it's okay to continue, but if you are fed up with it, we can break. Okay. Break 5 minutes and then 40 minutes more of this torture, okay?
with the lecture. So our outreach group is planning to take pictures and put them on social media. If someone doesn't want to appear, they should let us know so that we avoid putting unwanted pictures online. Thank you.
Okay, so I think we can start with the reminder of this lecture. Yeah, so in discussing estimators, as you have seen, it's not trivial. Sometimes it's good to spend some time on the right choice for your estimator. There are things that that you should strive for, and in fact, there is one acronym here. The UMVU is paradise. Okay, if you get there, that's okay. The uniformly minimum variance unbiased estimator has it all, right? Because you are unbiased, but it's the one among the class of unbiased estimators which has the smallest variance, and therefore you should definitely use it if there is there for you, but you sometimes have to find it. And in fact, here is another point where knowing statistics will guide your hand towards finding the best thing and make you a better physicist than your colleagues. And of course, the form of this estimator depends on the distribution. So it's not there for you to pick up. You have to understand. So two properties that are related to being the UMVU are efficiency and robustness. And we talked about this, I think, already. In fact, efficiency, we said what is an efficient estimator, but we can be quantitative, and efficiency is the ratio of the variance of your estimator to the one that is the minimum. Well, there might not be one that has that in fact hits the minimum variance bound made by the Rao-Kramer-Frechet. But you have a bound, you know, the RCF one, and so you can actually define the efficiency as the ratio of the variance of your estimator to the minimum variance bound. And the robustness, which we talked about, and we'll talk about it in a second now. So the sample mean is the most used estimator for the center of a distribution, and rightly so, because in most cases, but also in general in asymptotia and for a Gaussian distribution, the sample mean is the maximum likelihood estimate, and it's the uniformly minimum variance unbiased estimator of the location of the center of a distribution if this distribution is Gaussian. If the distribution is not Gaussian, well, then no, it may not be the best choice. And the sample mid-range is something maybe you have never encountered before. It's, well, you have some values along an axis, and you take the center between the smallest and the highest one. Well, it's an estimator, but it's a kind of a strange estimator if you think about it, because if you have 100 points, this guy looks only at this point and throws away all the information in between. So it must be a large variance one if you think about it, because it's only relying on 2 points. Yes, these are the extrema, and the extrema are built on top of having a distribution of 100 points, but it only uses the location of these 2 points. So how can it be a smallest variance distribution? Well, it is in some case. It is the uniformly minimum variance unbiased estimator of the mean of a uniform distribution. So if you have a uniform distribution and you want to locate it, this is the box location problem, where you have data along an axis and you have a box. This is your PDF, and you don't know what the PDF is, and so you have some data where what is the center of this distribution? You could take the sample mean, and probably it would come out here, or you could take the sample mid-range, and it would would have to take this value here. And you see that, in fact, it does a better job for the uniform because the uniform doesn't contain any information here. So what you're throwing away, all these points here, it looks as if you're throwing away data, but you're not, because they don't contain any information, because it's uniform that they're sampled from. So both sample mean and sample mid-range are efficient. In fact, their asymptotic efficiency is 1. They converge to the Rao-Cramer pressure bound for the Gaussian and for the box respectively, but for other distributions, they are not. And one other thing to note is that if they are robust, the estimators have an efficiency which may not be 1, but it is less dependent on the actual distribution that the data are sampled from. Okay, so let's look at what this all means in a practical example. And the practical examples I'm going to make is the superluminal neutrino claim that was made in 2008 by the OPERA experiment at the Gran Sasso laboratories. You know, there's a CNGS neutrino beam that gets directly under the rock. Some people claim that there's a tunnel, there's not, but that's a long story, but okay. They travel 700 kilometers under the rock, and then they hit the OPERA experiment in the Gran Sasso cavern. And this experiment wants to measure the tau neutrinos appearance in this beam of muon neutrinos. But among other things that they were doing was to measure the time it takes to this beam of neutrinos to go from one end to the other, to check whether they travel at the speed of light or what. And of course, if the neutrino has a mass, it will travel a little bit slower, well, but immeasurably so. So they came up with this measurement where they took differences in time from the expectation from light traveling in vacuum, okay? And this difference is positive if the neutrinos arrive earlier than what predicted from light in vacuum. And you see they have 20 neutrinos, because these things have a small interaction rate, and they collected this data and they went on to measure the speed given these 20 neutrinos. And so they did so by taking the average of these 20 timing measurement. So they took the sample mean, all right? So the point to know, and they knew, of course, as I do, that these neutrinos come from the CNGS beam, which is a bunched machine, which showers protons on a dump, and then the neutrinos come up, and the protons come in bunches which are basically square functions. So they are uniform distributions, and in fact, you sort of see it here, right? They come from a uniform distribution. So when I saw this presented in Padova for the first time, I didn't even let the speaker finish his slide, and I said, why did you use the sample mean? And this guy was like, why, what? And because to me it was evident that this was suboptimal, but these guys didn't know it, okay? So this is a collaboration of several, I don't know, maybe 200 people or so, and nobody came up with the idea that they should use a different estimator for the location of this box. Because in fact, the best choice of the estimator is the mid-range, which has the uniformly minimum variance unbiased value, and it's only taking these two guys and taking the midpoint, okay? And so this takes me aback, and so if they had used the sample mid-range, I wanted to know by how much they blew up their estimate of the neutrino speed uncertainty. And so I did a pseudo experiment with 20 neutrinos. Now here's a small detail. In this case, the number of neutrinos that you collect makes a difference, because 20 is a number not so different from 0. So you should condition, if you want to ask the question, what is the uncertainty that OPERA could put if they had used the mid-range? In general grounds, not looking at the actual measurements that they did, but sampling from a uniform. if you ask this question, you should condition to the actual experimental conditions that allowed them to derive their own results. So you're not going to say, okay, they saw 20 neutrinos, but if you redo the experiments a gazillion times, sometimes you get 24 and sometimes you get 17. No, you need to condition to the actual conditions which derived this uncertainty from their data set to get the most precise inference on what you want. That is to say, conditioning allows you to reduce the sample space and make your inference more precise. We will see this more in detail in tomorrow's lecture, because this is an important point which is very, very little known, and I think you will benefit from knowing what is ancillarity and conditioning. But okay, let's get back here. So you see that if you sample many times 20 events from a box distribution, and then you take the mean and you do this a gazillion times, you get a parabola in semi-log space, which is basically Gaussian, of course. While if you sample this mid-range, you get the Laplace distribution, which is the joint of two exponential fall-offs. And you see that one of them is definitely linear than the other because it's the UMBU. And in fact, they could have halved their uncertainties if they had used the sample mid-range. Okay. All right. However, again, if you look deeper in the problem, you will find more interesting conclusions. So, is this really a box distribution that they have? Because we have seen that with a box, you have to use the mid-range, and with a Gaussian distribution, you have to use the mean. Now, you know that these protons are bunched with a box distribution, but then you also know that in experiments there are jitters, that is uncertainties. These protons do not all come like a single man on your target, right? So if you want to model these details, you will get to know a little bit more about the actual conclusions. In fact, each timing measurement is not exactly equal to the others, because there are additional random smearings. So if you're an experimentalist, you may know about these things, and you may try to model into your toys that allow you to study the properties of your estimators, which is something you should do if you are an experimental physicist. Now, I don't know how many of you are experimentalists and how many are theorists, but even for a theorist, it is good to know these things, because you are sometimes in a situation when you want to sample the properties of your uncertainties on something. Okay, so the random smearings on the timings do affect our conclusions because they modify the PDF. It's not a box any longer, it's a box with some smearings. So what should we do? Let's model it, right? We can do it. So we take this box distribution, and then we smear with a small Gaussian offset smearing, and we vary this smearing, and we look at the values that we were quoting before, the uncertainties from the sample mean and the uncertainty from the sample mid-range, when also the sample mean gets affected because the 25 nanoseconds wide Gaussian gets smeared also a little bit. But you see that the mid-range properties are less robust than the properties of the Gaussian, and that should not come as a surprise, because the Gaussian is really the converging distribution of everything in statistics, and so it is inherently a little bit more robust than other things. So the sample mid-range is perfect for a box, but it's increasingly less than perfect when the box is smeared. Okay, and if the smearing is large, this becomes a Gaussian, and the Gaussian will have the sample mean be a good estimator, while this will be less good. Okay, so we learned a little bit from this toy. We learned about the robustness of your estimators. The point, though, is not whether Opera should have used the sample mid-range of the sample mean. The point is that nobody did this study before quoting the result, okay? Well, you should, if you have care in constructing your result. Okay, so much for efficiency and robustness. Now, I promised that we would look into the problem of weighting average with correlations. And so it's a tough thing to look at before lunch, but we will try nonetheless, okay? So we said that Taylor series expansion is good. It allows you to get variance estimates for derived quantities and blah, blah. But this linear approximation that you get in the covariance may lead to strange results sometimes. So let's consider the least square minimization of two measurements of the same physical quantity K. Now, let's forget, this is not a Poisson measurement, okay? So this might be sampled from a Gaussian. So it's okay to use the least squares. And let's try to consider a case where these two measurements of the quantity have a common offset error. So that is to say that you want to measure a certain physical quantity that has a certain value of theta true here, and you are going to sample something, and this something there's a bias. So your measurement has a common offset error. This bias, this positive or negative bias in the quantity is common. So if one measurement is low, also the other one is low. In fact, I should not have written it this way, but I should have shown a two-dimensional distribution where if you are measuring one on one side, the two measurements basically are not independent. So you measure x1 and x2, and they are correlated, okay? So if this is the true value, when I get x1 larger than the true value, also x2 is likely to be larger, okay? Do you see it? Yeah. So whenever I sample a certain value of x1, I am also sampling a distribution of possible values in x2. And this distribution depends on the particular value that I took. Okay, so these two distributions are different because they are conditional on different values of the other quantity. So there is a correlation, so this makes things more interesting. So let's model the covariance matrix this way. We have a correlation term and the individual variances, which of course depend also on the correlation part, on the common offset uncertainty. Now, if this is the covariance matrix, the 2 by 2 matrix can be inverted. This 1 over the determinant D minus B minus A, whatever it is, and you can get this expression. Nothing to say about it, and you plug this in the expression of the chi-square, which you remember is a sum of terms of one variate times the inverse of the covariance times the other variate, and you get this chi-squared expression. I really would insist that you do this with paper and pencil once in your lifetime, okay? Because you learn stuff. Do it once in your lifetime if you haven't. Because it's algebra, so it takes only 10% of your brain, and you can think of other things while you do, but you learn things about the structure of your problem, okay? So this is the expression you get, and if you minimize this chi-squared, you get the best value for the common, the fit value, basically, and the uncertainty. And you see how tidy and neat this is, because we get exactly the same result for the weighted average without correlations, and we are very happy about that. Basically, the correlation has not spoiled our measurement. But it has indeed increased the variance, and it has increased the variance in a way that we could expect. These two guys get measured with an uncertainty in addition, and therefore they should pay the price in the common variance. So we come up with a lighter heart because we think we have understood everything, right? Now, let's look at the normalization error now. So let's imagine that the two variables are correlated by a common normalization uncertainty. What it means it's that there is a scale. So if one of them is biased I, the other one is biased I by the same fraction, not by the same additional amount. Okay, it should not be so different, right? Let's try. So let's write the covariance matrix this way. We have an additional to the variance of the first term, which is a scale factor times the value that I actually measure, and the same for the second measurement. And then there is this correlation term. And this is only one of the ways that I could write this covariance matrix, but it doesn't make a difference, as I will show in a minute. But in any case, this is a scale factor that is smearing out your measurement uncertainties, right? And I can invert this covariance matrix very easily, and I get this expression. And then I plug it in the chi-squared with the matrix expression we saw 20 slides before. And this time, the minimization produces these two results for the mean and the uncertainty. So there is this funny denominator which has a structure which we now say, okay, there's a scale factor. It plays at the denominator, so it is liable to bias low this value, and it depends on how different these two numbers are. But okay, if you just look at the expression and say, okay, this is what it is, I didn't do any mistakes, so fine, good. So let's try it out on an example. I have 10 plus or minus 0.5, 11 plus or minus 0.5, and these two numbers have a 20% common scale uncertainty. I do the math, and the result is 9.7. Does any of you get surprised by seeing this number? Is it surprising or is it normal? The first time I saw it, and I was more or less your age, I was surprised. How come I have two numbers and I make the average and the result is outside the bounds? It fights my common sense, okay? But it is correct. It's the answer to your problem, and we'll see why that arises, okay? So let's take the problem by taking the ratio from what we expected without correlations to see what is going on. So the ratio of these two is this, which at the denominator is 1 plus something, and this something which increases the denominator, so it shrinks k with respect to x, depends on how different the two values are. This doesn't really ring any bell. Of course, it depends on the scale factor uncertainty. But we don't gain a lot of wisdom, but let's see what we can conclude so far. If the two measurements differ, their square difference divided by the sum of their individual variances increases the denominator by the amount allowed by the scale factor. So the least square fitting squeezes the scale in order to minimize the chi-square. So that is to say, I see the two numbers are different. The chi-square fights the fact that these two numbers are different, so it allows the fit value to be smaller such that the chi-square itself gets minimized. And this is in fact due to the fact that the square expression is using the first derivative of the covariance, because the two variances do not get rescaled when the normalization factor is lower and the points gets closer so that the chi-square is minimized. But okay, this is only particular of this particular case, but it is reminiscent of the Neyman's chi-square. You remember that you put in a Poisson likelihood the actual values that you measure, like here, you put the actual values that we measured in the covariance matrix, and we get this strange result. So let's look at a little bit why this does in fact make sense. And let's look at the general case, because that particular case is plagued by having looked at that particular covariance matrix, but it is a general property that we get this kind of behavior of the result of an averaging getting outside of the bounds. So we get a covariance matrix in a most general form. I can write it. with the correlation coefficient rho, and then I get the weighted average by the same method that we saw before, and it's this expression. Where you see that the two weights of x1 and x2 are this complex expression of the variance and the correlation coefficient, and the variance, or better, the inverse of the common variance is the inverse of the first variance plus this term times this. This is interesting because I have factored it out in a way that tells me that the common variance, in general, the inverse variance of the combination is going to be smaller than the variance of the first measurement, so that the inverse is larger, only if this doesn't get to 0. But this can get to 0 if rho is the ratio of the two variances. Okay, so there is a case, first of all, when if I have two measurements, I take a measurement with sigma 1, and then I take a correlated measurement with sigma 2, and because the ratio of the two variances is such that that becomes null, it's like I didn't take the second measurement. It doesn't reduce the common variance. Quite peculiar, huh? And what happens if the correlation coefficient is even larger than the ratio of the two variances is that this weight becomes negative. And therefore, if one of the weights is negative, then the average goes outside of the bound of the two measurements. And the reason for this behavior is that when there is a large positive correlation, the two results are likely to be on the same side of the true value. They go along with each other. And this is the maths that proves it. But let's imagine that we are discussing this among friends. And so we will try to follow the logic here. John says, I took a measurement and I got x1. I'm going to take a second measurement, x2, if it has a larger variance than the first. Do you mean to say I will more likely get x2 larger than x1 if the true value is less than x1, and smaller than x1 if the true value is larger? And Jen says, yes, that is correct. Your second measurement goes along with the first because your experimental conditions made the two correlated with one another. And x1, as you said, is more precise, so it has to be closer to the true value. But that means that my second measurement is utterly useless, says John. Wrong, says Jane. It will in general reduce the combined variance. It will not do so only in a particular condition. Okay? Least squares estimators are consistent. So the weighted average will converge to the true value in large sample limit, except when we are in this very particular case. And John says, I still can figure out how on earth the average of two numbers can be outside of their range. It just fights with my common sense. Jen says, you need to think in probabilistic terms. Look at this error ellipse. You have two measurements, the ellipse. This is thin because there is a correlation, and it is tilted. And it is thin because one of the variances is much smaller than the other one. Okay, so please pick a few points within this ellipse. Okay, so tell me whether they are mostly on the same side or on opposite sides, so the two deviations are both positive or negative from the true value. Ah, sure, all but one are on orange areas. Yes, that's because their correlation makes them likely to go along with one another, right? And I can actually make it even easier. Take a two-dimensional plane, draw axis, draw the bisector. This represents the possible values of the true value. Now we draw the error ellipse at a point on the diagonal. Okay? And now you enter your measurements A and B. This corresponds to picking a point within the ellipse. Okay? Suppose you got A greater than B. You are on the lower right of the plane. To find the best estimate of mu, you move this ellipse along the diagonal because the center represents the true value of mu. And what a chi-square does is minimize this ellipse while keeping it on the diagonal because it wants to minimize it, and have a tangent that is on this point here. So that is to say, basically, that within all the ellipses that you can draw with this particular tilt and the dimensions, and the relative width of the two axes, within all this infinity, you have to choose the one that passes through the point P. And this is the only ellipse that does this. And okay, in this particular case, the point lies more or less at B, but probably even a little bit smaller. Okay, so we are interested in the smallest ellipse because the chi-square does exactly that. And the center gives the best estimate mu. And so John says, oh, now I see it. It's bound to be outside of the interval. This is a more precise construction where you see that this is a bigger ellipse that fulfills the criterion, but the smallest ellipse that passes through the point is here, and this point is outside of the bound. Okay? Yeah, so it is outside of the interval only because the ellipse you have drawn is thin, and because its angle with the diagonal is significant. So the two variances are different, and the correlation is large. In general, the result depends on how correlated the measurements are, as well as on how different the variances are. Okay, and note also that in order for the results to be outside the bound, the correlation must be positive. This is a particular case. Okay, so this is the construction. And if I have 2 more minutes, how much time do I? Okay, perfect. I'm clockwork today. So this is an example from the CDF experiment that collided protons versus antiprotons at the Tevatron at the end of last century, well, until 2010, in fact. But this example is from 1998, and I was a reviewer of this analysis. And this is a measurement of the cross-section for measuring jets of very large energy. You collide protons, they make jets, you measure the energy of the highest energies, the jets that you see, and you plot a histogram. You plot a histogram of all the values of jet energy, and it's a steeply falling distribution over orders of magnitude as you go towards 450 GeV, which was the highest energy jets that you could see. And you can model this with QCD, quantum chromodynamics, and these QCD models will depend on the parton distribution functions inside the proton, which tell you how probable it is that you smash quarks or gluons with a certain fraction of the proton's momentum. And so you have all these models and you have your data, and you can compute the ratio of your data divided by the model, okay? And it should be something centered at 0. This is if the standard model CTEC4M is used. And the data point, you see, unfortunately, you cannot see the uncertainties, but okay, there is a statistical component of the uncertainties of these data points. And then there is a systematic uncertainty band that is all over them. But if you divide by different models, not by CTEC4M, but by all these other models, you get different theory models that you compare your data to. Okay? So the name of the game is, given this data with some statistical uncertainty, which you cannot see, unfortunately, and some systematic band, the name of the game is to decide which of these 4 models is the 5 models, because this one at 0 is also one model, is the best fit to the data. And so it was rather surprising to me. Well, first of all, forget this thin curve which was derived later, because the original plot didn't have this, which is the high jets PDF, which was cooked up expressly for fitting this data later on. So you have these 4 models. And the question is, what is the chi-squared of the data with this model? What is the probability of these models with respect to the data? First of all, you see that the data are above all the models, which in fact made this interesting because the data might imply that there was some contact interaction in addition to QCD, which made more jets at high energy. So in fact, CDF had ventured to speculate that there might be preons inside the quirks, it didn't publish anything along those lines, but there was a media storm. You can read this in my book. But anyways, these four models, which one fits the data better? If you have to choose which of these four models, you should know that in addition to statistical uncertainties, which are a little bit smaller, these systematic uncertainties are more or less correlated, because there's a jet energy scale which shifts the scale of all the measurements of the jet. Would you choose the CTEC4M, which is the closest to the point, or would you choose this one, or this one, or this one? Which one has the best probability in your opinion? I know that this question has too little data for you to give an answer to, but I was surprised because the one that gives the best fit is MLST, which is this guy here. This curve gives a significantly better fit than this one or this one. I find that surprising, don't you? It is surprising because you say, but it's way farther away. Yeah, but what matters is not how far away it is, because, see, this systematic band applies to all the points. And it allows for 1 sigma shift to go down by here. And to go down here, you need to pay 2 units of chi-squared. Not, well, 4 units, but not 1 sigma per point, because there's a full correlation between the points, because the systematic shift the scale of everybody. And so you pay a small price to get down here, but then this slope is more or less reminiscent of the statistical dispersion of the data points. So the bottom line is that chi-square by I fails when there are correlations, because you cannot any longer take into account the fact that you can have coherent shifts of the data and then stochastic variations of the statistical uncertainties. Okay, so be careful when there are large common systematics in evaluating by I the consistency of a set of data with a fit, because you're going to make it wrong more often than not. Okay. Okay. So questions. Where is the restaurant? Okay. The questions can also be asked by email, of course. Okay, I'm done.
Thank you very much.
So yes, take care, because it takes a minimum of half an hour to go downtown where all the restaurants are. No? So please take into account that we have to come back at 4. Mm-hmm.